All right, let's look at this following eigenvalue problem, and I'm going to try to find all possible eigenvalues. All right, so differential equation is y double prime plus lambda y is equal to 0, and the boundary condition is y of 0 is equal to 0, and y of L is equal to 0, and assuming that the L is a positive number. All right. So let's look at the three cases, right? So let's check to see if lambda equal to 0 is an eigenvalue, right? So if lambda is equal to 0, then differential equation is just y double prime is equal to, I'm going to use blue here, all right? So y double prime is equal to 0. By taking the antiderivative, we know that the y prime is going to be some sort of constant. So I'm going to call it maybe a, right? Then by taking another antiderivative, so we know that the y has to be ax plus another constant. So I'm going to use b here, right? So solution should be a linear function, right? Then we want to check y of 0, right? So if you plug in 0 into that, you're just going to get b, right? But this has to be equal to 0, right? So b is already equal to 0. So how about a? So let's try y of L. All right, so I'm gonna, b is equal to 0, so I'm gonna drop that out. So it's gonna be just a times L, and this has to be equal to 0, right? But again, we can simply divide through by L, since L is just a positive constant, so you end up getting a equal to 0. All right, so from there, we know that a is 0, b is 0, so only solution you have is y equal to 0. So this is a trivial solution. Right, so which means that lambda is not, so I guess here, so therefore lambda equal to 0 is not an eigenvalue. Right, so that was case 1. Right, so let's look at the case 2. Let's say lambda is going to be a negative value, right? So I'm going to, for simplicity, I'm going to let the lambda equals, so it's negative, so I'm going to do a negative alpha squared, right? And that way, characteristic equation is going to be r squared minus alpha squared equals 0, right? So we know that this is going to be, r is going to be plus or minus alpha, right? So this would give us the form of the solution. It's going to be y equals a. It's e to the, right? So alpha x plus b times e to the negative alpha x, right? Then let's check the boundary condition. So y of 0, right? So you have e to the 0 is 1, so you're just going to get a plus e to the 0 again. So a plus b must be equal to 0 from the first boundary condition. And let's look at the second boundary condition. So you have a y of L is equal to a e to the alpha L plus b e to the negative alpha L, right? Then what we're going to do is, we know that this has to be equal to 0 at least, right? Right? Then we have to try to solve for a and b using these two equations. And I'm going to actually multiply here. So I'm going to multiply by e to the alpha L, right? Then you're going to get a e to the, I guess, 2 alpha L plus, all right, so this and e to the negative alpha L and e to the alpha L cancel out. So you're just going to get the B, right? The sum is still going to be 0 because 0 times anything is 0, right? Then what we can do is we can maybe subtract the a plus b from there. So I'm going to do here a plus b is equal to 0. So I'm going to do the subtraction, right? Right, that way b is gone, and here we have a, and you have e to the 2 alpha L minus 1 is equal to 0, right? Then here, one thing you have to notice that the e to the 2 alpha L, 2 alpha L is not going to be equal to 0. So we know that e to the 2 alpha L is larger than 1. So this is greater than 0. So which means that we can divide through by e to the 2 alpha L minus 1 to get a equals 0, right? Then here, we can plug in 0 into this equation, so b has to be equal to 0 too, right? So which means that you have only one solution, which is a trivial solution, right? So again, this is a trivial solution. All right, so it looks like case 2, when lambda is negative, there is no eigenvalue because we have only trivial solution. All right, so let's look at the third case. Lambda is positive, right? So since it's positive, we can let the lambda equals alpha squared, right? Then do the characteristic equation just like before. So we have r squared. Now it's a plus alpha squared is equal to 0. And this means that the r is going to be equal to plus or minus alpha I. All right. All right. So we have a solution, have this form. Y is equal to a cosine of alpha x plus b sine of alpha x, right? So let's check the first boundary condition. So y of 0, since cosine of 0 is 1, so you get a, and the sine of 0 is 0, so it drops out, and we know that this has to be equal to 0. So a is equal to 0. So we can scratch this guy out. And let's try different color. Y of pi, actually not pi, y of L. And this is going to be equal to b sine of alpha L, right? Then we want to make sure that this has to be equal to 0. So in order to have a non-trivial solution, we don't want b to be 0. So only way that can happen would be we have to make sure that this guy is equal to 0. All right, so which means that we have to make sure the angle, which would be alpha times L, this is going to be equal to, all right, sine is going to be 0 when angle is a multiple of pi. So we have n pi, right? So so where n is any integer, right? All right, so since we're looking for a lambda is just alpha squared. So let's just try to find alpha first. We can just divide through by L. So alpha is going to be equal to n pi over L. All right. Then if you want lambda, right, so we can just square both sides. So it's going to be lambda, which is alpha squared, which is n pi over L squared. All right. So this is the eigenvalue. So I'm going to actually, since it depends on n, so I'm going to call it lambda n. Right. So this is the eigenvalues. All right. Then the following eigenfunction would be, I'm going to call it the y sub n. All right. So it's going to be a sine of, all right, alpha is simply n pi over L, and then x. All right, so this is the eigenfunctions. All right, so those are the eigenvalues and the eigenfunctions. Maybe I'll just box it in. All right, so here. All right. So those are the all possible eigenvalues and eigenfunctions of the given eigenvalue problem. All right, that's it. I hope that this was clear.